Yes. Yes. So, as just said, understanding aggregation of proper learners in multi-class classification, and this is joint work with Julian Asilis from University of Southern California, right here, and then Grigoris Velegkas from Yale University, down there. Good. So I will actually quickly go through some slides from earlier today to motivate some of our work. So we saw earlier today binary classification, so we got pictures of animals. We wanted to guess their species. No, not species yet. Whether they were a mammal, yes or no, and we would have this learning algorithm taking in some labeled sample. And then we had some prediction algorithm, which was chosen based on this labeled sample, so it would look something like this. The learning algorithm gets the sample, and then it predicts some prediction algorithm. And then we had the assumption that these labeled samples come from some data distribution. And then the goal of our learner was to produce some predictions from new examples from this data distribution with a small error. Okay, and formally that was, we had some input space X, some output space 0, 1. Then we had some learning algorithm taking in that labeled sample and outputting some mapping from our input space into our label space. And then we had some data distribution P or X, and then we were in the realizable case, so we assumed that there was some known function class of BC dimension D, and we had some unknown labeling function H star in there that we wanted to learn, and the way we were able, the clue we were given to learn this function was this labeled sample. And then we defined this error function, and that's the probability of some classifier being incorrect on a new training, a new point. And then the goal was to minimize this error. Okay, good. And as we saw earlier, in the binary classification case, this is characterized by the VC dimension, and we saw that the empirical risk minimization, so some algorithm outputting hypotheses within the hypothesis class, which is consistent with the labeled sample, got this error, and this was with probability 1 minus delta, and this was due to Vapnik and Chivanenkis and Blume, Voigt, Hausler, and Warmuth. And there was also, there's several low bounds, but this is the strongest, and this is by Busquet, Haneke, Moran, and Chivotowski. Right. So this was the picture of doing EM/proper learning, so just outputting something in the function class. But we also saw earlier that if you do more than proper learning, then we only had this lower bound without the log term up there, and then we saw that first Haneke removed this log factor with a clever subsampling scheme, and then running EM on each of these subsamples and then taking majority. Later it was shown that you could also do backing, where the algorithm is due to Breiman and the analysis due to Larsen. Look something like this, and it was also recently shown that by aggregating just 3 proper learners, namely majority of disjoint, like EM trained on disjoint training sequences, then in expectation, not with high probability, you can get a D over N bound. There's also other optimal learners, which is more refined in the aggregation, such as one inclusion graphs and iterates of them. But for this talk, we will talk about simple aggregations. Good. So this was the learning landscape in binary classification. We saw that the landscape is pretty well known, and there was some gain of aggregating proper learners. So let's go to the multi-class setting. So what do we change? Now, instead of trying to predict whether the animal on the picture was a mammal, yes or no, now we try to predict its species. So now we have more labels, and we still get a label sample, just with more labels now, and then we go down the list, and then we come to this known function class. But now we have VC dimensions standing up there, and that is heavily dependent on binary settings. So which kind of dimension should we look at in a multi-class setting? All right. And that brings us to the next slide, which introduces the Daniela-Schwarz dimension. And what is that? That's the largest integer such that there exists a point set of size d and some subset of the hypotheses such that this subset is finite, and that for each f in f, it has an ith neighbor g. So what is an ith neighbor? That is, g is an ith neighbor of f if it is the case that f and g agree on all these indexes up to ds except I where they disagree. So in a picture that would look something like this. So if we have f here, and we have 3 data points, x1, x2, and we have g which disagree with f on the first point, then this would be a first neighbor, and we have g2 which disagree with f on the second point, then this would be a second neighbor. Good. So you can define this dimension, and then it have rather recently been shown that this dimension actually characterizes multi-class learning. And the upper bound was shown by Bruking, Kamon, Dinor, Moran, Yuhadayev, and they gave an algorithm which obtained this upper bound. Recently, it was also sharpened by Haneke, Moran, and Zhang. We also have a matching lower bound by Daniela and Schwarz. So the DS dimension characterizes learning in the multi-class setting, but actually also in the work by the later. It was shown for any proper learner, there exists some learnable problems, so with finite DS dimension, which is not learnable by this proper learner. Right. So that leads us to the next dimension we will consider, which is the graph dimension of H, which at least make proper learning possible. So what is that? That is that there exists some integer g and some number of points, and then some function in H such that there exists some subset, for every subset in these set of indices, there exists some g which agree with f within the indices and outside of the indices disagree. Okay, so from our example before, where we will now only consider the 2 first points, then we see that here f and g agrees on the first point, so this would be the subset 1. Over here, g1 and f2 disagree on, agrees on the first point, so that would be I1. F agrees with itself on 1 and 2, and then we could add a third hypothesis, and then this would disagree on 1 and 2. We are currently restricted to 1 and 2. Then one can look at this example, and then one can see that this actually only have DS dimension 1. So this is trying to remark that the DS dimension is less than the graph dimension. So from the previous slide where we said that we can have classes which is learnable, but not necessarily by a proper learner, this is at least intuitively the reason. Good. So what does the graph dimension characterize? Well, when we have finite graph dimension, then we know that we can learn by EM, and we can learn with this rate. And this is due to Natarajan and Ben David, Sisibianchi, Hausler, and Long. Furthermore, it was shown by Daniele Sabato, Ben David, Charles Schwartz, that there is a lower bound over here for learning with EM. Right. Good. So this brings us to the question we tried to answer in this work, which is what can we do with aggregation of proper learners in multi-class classification? Good. So there's 3 bullet points. The first one is that we show a general reduction for majority voters of EM, and this reduction is general enough to capture the result by Haneke, backing a majority of 3. So we get, with high probability, in the case of Haneke backing, this error bound, And then if we consider majority of 3, we would get an error bound of d over m in expectation instead. Our second contribution is to give a lower bound instance which separate learnability, aggregation of EM, and EM. Okay. So what do we mean by that? So we give a lower bound instance which has a ds dimension of 1, so it's learnable. We show that there exists an EM algorithm which from the upper bound has this error with plus log 1 over m, and there's a matching lower bound. And lastly, we show that this EM learner has a matching lower bound here. So we get a gap between learnability and majority of EM, and then just running EM. And the last contribution is here very high level. So we give a lower bound instance for any algorithm aggregating / stitching together a constant number of hypotheses, and show that such an algorithm on this lower bound instance must have expected error constant. However, this lower bound instance is again of ds dimension 1, so it is learnable. And that's it.
I think I'm loud enough.
Okay.
Yeah, before question. Yeah, is there any question in the room? I think we have maybe 1, 2 slots for 1 or 2 questions.
I don't need the mic.
You don't need.
So I think proper learning is not sufficient for multi-class learning in general.
Yeah.
Do you know what characterizes proper learnability in multi-class problems? So the graph dimension is sufficient. Is it necessary?
I think it's not possible. I'll talk about this.
Okay, come to the last session. Okay. Not possible? What do you mean? Like there's no dimension?
No, like, character hypothesis.
Oh, okay.
Maybe some question that we can answer immediately. I have a question. Like, what is like all this teaching? Maybe I didn't fully understand it. Like when you were saying that if we aggregate together only a constant number of hypotheses, but what about the majority of 3? Segregation of
Yeah, for instance, that would be stitching together 3 hypotheses.
and you're saying that there is an example where the error of stitching 3 will be constant, while sample complexity of some more involved learner will be 1 over it. So there is no way how majority.
Yeah. And it's basically, if you define it properly, then this lower bound is actually saying that you have to stitch together infinitely many hypotheses to not.
Stitching is any function of.
It's kind of like your image. You can okay. So for some sample, you get some function. Now you want the property such that when you look at the smallest subset of H, which contains the image of F, then this has to be infinite.
Any other questions? Let's thank the speaker again.